Okay. Before we get into the core science of the title of the presentation, which is a blood sugar wireless and passive MEMS-based sensor, I think the word MEMS has been presented by my colleague Mahmoud in the previous presentation, so I will skip that. But I want to introduce to the problem which brought us into this sensor before we get into the core science. Most of us know people who got diabetes. Diabetes, which what we commonly call as blood sugar. Anybody in this hall know a person who got diabetes? Be glad if he raises his hand. So there are people who know people who got diabetes. If we look into the demographic of this disease, we will find that according to the International Federation of Diabetes, there are around 370 million persons around the world with diabetes. Not only this, but there is a bad fact about it. There are 4, each 5 of those guys is in a low income or a middle income country. So not only these people are suffering a very bad disease, but they don't have enough money to pay for its treatment. If we get back to this map, we'll find that there are around 34 million persons in North Africa. Not sure about this word. There are around 34 million persons in Africa with this disease. How we fight diabetes? Mainly, there are 2 types of diabetes, type 1 and type 2. Type 1 is where the pancreas totally stops producing insulin into the blood. So the blood does not get what he needs of insulin to control the glucose levels. And type 2, where the body naturally possesses some sort of resistance to the insulin provided by the pancreas. Type 1 and some cases of type 2 requires treatment by insulin shots. So a diabetic person will have to move around with a syringe. He will have to keep it in a temperature-controlled environment. And not only this, but he will have to suffer the pain daily of the shots. The bad thing about it is that if he even goes by the book and follows whatever the doctor is saying, he will suffer in the long run, or most probably, in most cases, suffer in the long run bad complications. These complications are not minor ones. I'm not talking about itching or something like this. It's severe complications. They might have impaired eye vision. They might have a common complication which is known as diabetic foot. Diabetic foot is a complication that requires the removal of a patient leg. So imagine a person who had type 1 diabetes, because it mainly affects kids when he was, let's say, 12, and when he's around 35, he had his foot removed. Not only his life stops, not only he can't work anymore, but his family that he was a breadwinner for it will no longer be able to survive without it. So this disease that requires a better treatment. Breakthrough came within the last decade, which was the insulin pumps. Insulin pumps are electronic devices that the patient attaches to his belly or his belt, and then use some wiring to continuously monitor the glucose level in the blood and feedbacks it to a precision device that shoots back insulin in his blood. So the target of the insulin pump and the main objective of it is to completely override the pancreas function, which has stopped or is not functioning, maybe, let's say, malfunctioning, or the body possesses some resistance to the insulin it's provided. But the problem with the insulin pumps is that they are bulky, they're big, and they are very expensive. I know a friend, and I think he's in middle to a high income class, that asked him for one of them, and he found that the cheapest one was about 8,000 Egyptian pounds. So this is something that not anyone can afford. It's something that's very expensive and just doesn't solve it. You have to move around and give it due care. Oh, it might break. I'm attaching something to my body. It's not something good. So we decided that we have to do something about it. Okay, this is gonna sound like something utopian or impossible, but we identified that the need, what we need is that we need tiny cells that you will inject surgically in the patient's body, and then you will not have to do anything surgically for this patient. It should be once in a lifetime. This sensor should not require much power, or none at least, and feedbacks this wirelessly to a feedback system that controls the insulin in the blood. I know this is some sort of sounds impossible or something that can never be created, but we decided to exploit it by some way. First, we identified the challenge. The problem mainly lies in the power source in the insulin pump. You can even try this. Any electronic device mainly has its weight going into the favor of the battery. So if you remove your phone battery, you will find that it's thinner or light, and the battery is taking like 80% of its weight. So we need to remove this big battery and find an appropriate way of transmitting the information to this decision device that will shoot back insulin in his blood. This first step, which is the sensor, this is what we have been working on, and what I've been saying, the feedback method, and then this could be sent to something like a mechanical injector or something that shoots the insulin. So what we have been doing? Our sensor uses some phenomena known as surface acoustic waves. Surface acoustic waves are just like the name says, they're acoustic waves. Acoustic waves are like the waves I'm saying, just like the waves you're hearing right now that are coming from my voice. But they are a little much higher, not a little. They're much higher in frequency. They're around 100 megahertz, not 20 kilohertz as we speak. But we guide them on the surface of a special material that's known as piezoelectric materials. Piezoelectric materials are around us everywhere. They're just like the materials in a cigarette lighter, that when we push it, it starts, we do some sort of mechanical energy that is converted into an electrical spark that lights up the gas. But of course we don't use it here to light cigarettes, we use it to guide the wave over its surface. If you look at this sensor, we find that we have two sets of electrical transducers. And in the middle there is an active area. We send the wave from this side to this side. Whenever something occurs with this part, the behavior changes at the output. So how this works? There is a special type of polymers known as hydrogels. Hydrogels are just like plastic. Polymers have plastics in its category, but there is something significant with hydrogels. They are hydrophilic, which means it's a thirst for water. Whenever they sense water, they just want to get into its structure and expand. When they expand, they start loading the sensor. Thus, on the other hand, on the other side of the sensor, we read different behavior than the one we have been reading when there is no glucose in the blood, when there is no high level of glucose in the blood. So what we want to do with this device? We want to optimize this device to work in a way that we have the maximum output power on the other set of the receiving set of the transducers, so that we receive the maximum power. Not even this one have a linear operation around a specific frequency that would make this sensor work in the best way. We have been working for over than a year this sensor, and the results are pretty encouraging. I'm glad to share it with you. This is what's called the frequency response of the device. We are looking for the frequencies at which the highest amplitude occur at the output. The frequencies that have these highest amplitudes are known as resonance frequencies, and they are essential for the decisions which are taken in the design process. Not only we want just one high amplitude, but we want a mode shape that look like a wave. And unfortunately, we got a mode shape that just exactly what we want. This is a video showing how the sensor should operate. If you see on the left, we have the sets, the transducer of the input, and on the right there is the output. So the wave is being continuously transmitted from the left to the right. In the middle, we have the active area. So whenever something occurs in this active area, I receive a different thing on the right-hand side. So I can interpret this difference in a way that tells me how much glucose is in the patient's blood. So this is how the concept of this sensor works. When we came to linearity is the way we correlate the change in glucose to the change in the electrical signal. It means that if the glucose increases or decreases by one step, I want this same change happens to the electrical signal at the output of the sensor. We didn't expect something that good, but it happened. So this was nearly a perfect linear device, which it wasn't our target. Actually, we wanted to increase the power, but it happened. But until now, everything is going okay. Later on, we'll talk about limitations and trade-offs. It's not still a perfect device. But I want to present you to what's so special about this thing. The issue is that if we just get this sensor and plug it into a patient's body, we require a battery and some connecting wires for the input and the output signals of this sensor. It will not just work like this. I just put it, I'll need a battery, I'll need wires. And I don't think any diabetic patient will be glad to move around with wires going into and out of the body, or having to move with a big bag carrying the battery. So what we did is that we eliminated the battery and the wires. This is the core thing in this device. How did we do this? Surface acoustic waves are just waves. So instead of inducing the electrical wave using normal power, we use RF power, radio frequency power, that even your phone can transmit this power to the sensor, operates it, and the sensor responds to this phone wirelessly without requiring any external power source. So just as that simple, a phone can operate the sensor that is just implanted once in a lifetime into the patient's body, and the sensor responds to the phone, telling him what's the glucose level. So where are we right now? The problem lies mainly with the hydrogel. The hydrogel is a laggy material. It doesn't respond immediately. It takes about 15 minutes till it responds. We have found some alternatives that might take up to 10 minutes or 9 minutes, but our talking dream that I told you about is that we want to completely override the pancreas function. So we need a faster sensor. We are looking at nanoparticles and better stuff, but until now, this sensor is much more better than any existing sensing mechanism, because anything will require much more time. And the other issue that we are looking into is the choosing of a proper feedback system. We don't want to use the normal injectors that are currently existing because they are very painful and still does not achieve our goal and our vision of how diabetic patients should live. Thank you for your attention. I'm not sure how you enjoyed that.